Morning. Greetings from California. I'm Greg Scott. I'm Carolyn Roberts' brother. I'm a science teacher at Archbishop Mitty High School out here in San Jose. Carolyn asked me to talk to you a little bit about light. And I thought I would talk about several items with the properties of waves and the electromagnetic spectrum and all of that. When she asked me, I thought she was such a help for me as I made the transition from engineering to education that I thought anything I could do in return would be good. So we're going to begin today. I will share my screen. I do not miss distance learning, but this is a handy way to record a video. So let's pull this up. So we're going to talk about a few properties of light and waves. I'll begin by showing you some really cool tools that we can use to investigate properties of waves. Then we'll do a brief tour of the electromagnetic spectrum. And finally, I have a couple of fun facts and some demos that we can do with light and other electromagnetic waves. So a very handy tool is something called PhET, Physical Emulation Tools, out of the University of Colorado. I teach high school physics, but you can use these for all different levels. Today, I want to show you just a little bit about some properties of waves. We using these simulation waves on a string. This can run either on an iPad through an app, or you can run it on any laptop. These are HTML files. So I'm going to run the waves on a string demonstration. And we can look at this and see just a few properties of waves. I'm going to crank this up, get going a little bit faster. I'll stop it for a second. We can see something as we go through the electromagnetic spectrum. I'll talk a lot about wavelength and frequency. I just want to show you what these things mean. So you hear this wave traveling along on a string. If we look at the distance between one peak and the next, that length, that's what we call the wavelength. The frequency is just how fast any one of these beads in the string will bounce up and down. If we just watch one of the green beads, you'll see that it's bouncing up and down pretty fast here. It's bouncing down, up and down, just under 2 times per second. We can make a couple observations. If I crank up the frequency, if I get these bouncing really fast, notice how the wavelength gets shorter. See how the distance between the peaks is getting smaller. If, on the other hand, I bring the wavelength down, or if I bring the frequency down, then the wavelength gets a lot larger. Now, one more thing I wanted to show you before we'll leave this is if instead of having these waves just go off to infinity, going out through an open window, I clamp down the end, then we get some really unusual things happening. So I'm going to bring the amplitude, the height of the wave way, way down. I'm going to adjust my frequency. And I'm going to knock this wave down. I'm going to stop it, and then we'll get it going again. So you'll observe in this case, the wave is coming out, it's hitting this fixed end, it's reflecting, bouncing back. As it does that, this wave gets really strong. It starts to really amplify. The amplitude goes up quite a bit. If I go off of this value, then it's going to start to act kind of weird. You'll see things acting really funny, how it goes all wonky and out of place. So at certain frequencies, the wave will get very strong. This is used a lot in light with a phenomenon like lasers. I'll also show you an example how a microwave oven makes this thing that's called a standing wave. That's why you get hot spots and cold spots within a microwave. Okay, so that's just a little bit of basics on some waves. These PhET tools are extremely useful. I find them very, very good for physics and chemistry. We can use them for all types of education. So let's go back, take a look more at the electromagnetic spectrum. See, the spectrum, it goes from extremely long wavelengths, things that are more than a kilometer, more than 1,000 meters in wavelength. It's out in the radio wave spectrum, all the way through microwaves, infrared light. The visible light itself is just a very tiny part of the entire spectrum. Then we get into ultraviolet, X-rays, gamma rays, and so on. So let me try play this, yes. Now, at the highest and the longest wavelengths, the lowest frequencies, we have these radio waves. Wavelength is anywhere from a kilometer down to 1 meter. These are produced by having electrons in wires going back and forth. They get shaken back and forth very rapidly. That's how they come out from an antenna. They will produce the waves and they go off into the receivers on the other end. Now, back when I was growing up in Baltimore, I used to listen to a lot of different radio stations. A WCAO was a 600 kilohertz, frequency was 600 kilohertz, so the wavelength would be quite a few meters in that case. I was listening to WHFS in Annapolis, 99.1 and 99.1 megahertz. So that's a higher frequency and shorter wavelength. You get the at those large frequencies, when you get up into hundreds of megahertz, then the wavelengths get into about 3 meters. Now, your high school physics students can do all these calculations. The speed of light is 3 times 10 to the 8th meters per second. That's 300 million meters per second. The wavelength times the frequency gives you that velocity. So those types of calculations, we do these routinely. We ask our students to do that. I teach basically algebra-based physics, so I ask them to do that. And they can follow. I'm sure your students can do that too. Now, if we go on to the shorter wavelengths and higher frequencies, we get into a region called microwaves. That goes from 1 meter down to 1 millimeter. Now, our father worked for Westinghouse. He worked on radar systems. So he worked a lot with microwaves. He was very, very knowledgeable with that. These shorter wavelengths will reflect off surfaces, which is why radar uses them. They're also used in cell phones and in microwave ovens. I'll have a demonstration for you a little bit later to show you how you can measure the wavelength of the waves in a microwave oven doing some quesadilla physics. So we continue on down, you get into the infrared range. These are shorter waves out of the high end, about 1 millimeter down to 1 micron or 10 to the minus 6 meters in wavelength. Now, this radiation is given off by warm objects. Here we see a picture of the human body taken in the infrared. You can see the different temperatures in different parts of the body. Also, the James Webb Space Telescope, which has been just launched last Christmas, and we've just started collecting images from it. It uses the infrared range. The long wavelengths of infrared light means that light can pass through dust clouds. If you think of a good way to picture this is imagine as you're in a swimming pool and a little ripple comes along. That short wavelength on those ripples will bounce off you and reflect away. On the other hand, if you go out to Ocean City and you're out in the ocean, those big long wavelengths used to like to bob up and down the waves. They'll pass right through you as though you're not even there. So similar thing with the infrared, the longer wavelengths, they will pass right through the clouds of gas and dust. So we can see features that can't be seen in visible light. There's many, many pictures from the Webb Space Telescope. More of them are coming out every day right now. I highly encourage you to share this with your students. I'll just show you one of these right now. This is a picture of the Carina Nebula. Just an incredible picture. Now, this is a false color. The different wavelengths of the infrared have been turned into visible light so that we can see the pictures. The detail in the features are just amazing. You can see much more detail than you could possibly see in visible light, because again, with all the dust in these clouds, the visible light is blocked from that. So we can see stars, we can see where stars are being formed, and there's a huge amount. I could go on for hours on this, but I'll leave that for now. As we continue down the spectrum, we get to shorter wavelengths and higher frequencies. We get into a range of the nanometers, 10 to the minus 9 meters in wavelength. So anywhere from 700 nanometers to about 400 nanometers. This is the visible light spectrum, a very small part of the whole range. So this is radiation given off by very hot objects, one of them being the sun. The peak of radiation that comes out from the sun is in the visible light spectrum, what we see here on Earth. That's why our eyes are most sensitive to this. I spent a lot of time in graduate school working on both LEDs and detectors. We use transitions between the electron energy levels in atoms and molecules to both produce and detect light. So if you're teaching chemistry, I'm sure you've done some of these experiments with putting different elements into flame. You'll see that transitions between the energy levels will give off different light. There's a high energy, it will go toward the violet side of the spectrum. If there's a low energy, it will go toward the red end of the spectrum. And you'll see all this with fireworks also. They will burn those different metals in the different fireworks to give them their distinctive colors. Also, with visible light, the energy from the sun is used in photosynthesis. The light comes into the leaves. Mostly the leaves use the blue light. The green light is reflected. That's why leaves appear to be green. So what happens is that as that light comes in, chlorophyll will grab a water molecule, hold it in place. The light comes in, it tears apart the water molecule and uses very high energy hydrogen atoms then to tear apart carbon dioxide and make it into sugar molecules. The oxygen is left over. That's a waste product for the plants. They give it off. So fortunately, it gives us something to breathe so that our cycle of life can continue. Lots and lots of things you can talk about with your classes here. We continue down the spectrum, we get into shorter wavelengths. The ultraviolet radiation is anywhere from 300 nanometers down to 1 nanometer. This radiation is much higher energy. The electrons that absorb this radiation can get knocked out of an atom completely. These can break molecular bonds. In particular for us, this is a concern because it can tear apart the molecules within your DNA. So that will lead to sunburn. And in serious cases, if the DNA molecules are stitched back together improperly, then you can get sunburn. I'll include a link with this. There's a really cool Veritasium video on the world, what the world looks like in ultraviolet. I'll also show you how sunscreen blocks the ultraviolet. You can see it very clearly in this range. Continue on down to even shorter wavelengths. We get down below 1 nanometer all the way down to 0.01 nanometers. Now we're down to the size of an atom. This is X-rays. These can be produced, medical X-rays are produced by us shooting an electron beam at a very heavy element like tungsten. The transitions in the inner electrons will produce these. These will they will pass right through skin and blood and light tissue. They're absorbed by denser tissues such as the bones. If we go even further, now we get down into the gamma rays. If we get down below 0.01 nanometers, now we're down to the size of an atomic nucleus. Gamma rays are produced by nuclear reactions. They can penetrate all the way down into the bone. They can get into the bone marrow itself. So they can cause leukemia. Also, the gamma radiation really came about with the atomic age in the late 50s as the Cold War was developing. This certainly became part of the popular culture. The fear of nuclear war came into that. So many of these characters, like you see the Incredible Hulk, he was exposed to an atomic bomb blast, exposed to the full force of the gamma rays. So this is where Dr. Bruce Banner turned into the Hulk. And many other characters like this use that. All right, a few more examples, a couple of fun classroom demonstrations we can do with light, and we will stop there. Here's an experiment you can try at home. With your microwave oven, remove the turntable from the center. You might have to cover the knob in the middle part. I'll show you that here. Then take a tortilla, sprinkle some shredded cheese onto it, and we'll get ready to make a quesadilla. Put my plate into the microwave. Run it for about 20 seconds. And let's see what we got. So you'll see those annoying hot spots that you get, those hot and cold spots that you get from the microwave, those occur because of standing waves. What we can do here is let's measure the distance between a couple of the hot spots. I've got my handy dandy ruler here, and I'm looking down here. I think I can persuade myself that I'm seeing about a distance of about 6 centimeters between the two melted spots. You can see there's a hot spot, a cold spot, in the middle, another hot spot. Looking at this, I can persuade myself that I'm seeing about a 6 centimeter difference between them. It's a little hard to measure precisely because there's three-dimensional effects going on, but never mind. Now, your high school students can use the wave equation with the speed of light being 3 times 10 to the 8th meters per second. With that 6 centimeter difference, they can get the wavelength. They actually have to double that amount because it was a standing wave. That will become 12 centimeters. Take that speed, divide by the wavelength, you'll get a frequency about 2.4 gigahertz, which is the frequency of microwaves. And add a little salsa and have some lunch to go with your science. With a skinny fish tank and green laser pointer, we can demonstrate a few other properties of light. I mentioned earlier that light travels at a speed of 3 times 10 to the 8th meters per second. That's only true when it's traveling through a vacuum. If it goes through some other medium like water or glass, the speed will change. And if it comes in at an angle, then the angle will also change. So let's bring down the lights. I'll show you what we see. Here, I'm going to bring it into the water. If you do a demonstration like this, you can hold the laser up alongside the plastic, and you can see the beam of light coming in. You can see where it's coming in through the air along the plastic. When it hits the water, then it changes direction. This is called refraction. So we can see this both from above here. I'm coming from the air into the water. If I change the angle of the light, you can see how it's changing the angle going into the water. We can also go from water into air. If I come in underneath here, I'm going to come up, I'm going to hit where I hit the surface between the water and the air. A lot of the light reflects. You can get some really cool effects here. You can get multiple reflections. And some of the light continues on through, some of it will reflect back. If we go beyond a certain critical angle, all the light reflects. So you can actually change the intensity of the light that reflects. So, nifty little effect. Another fun FET demonstration is for color vision. I'll bring up, here I'm using the app on the iPad. I'm going to bring up the RGB, red, green, blue bulbs. We're going to look at some colored light. So here we have these 3 light bulbs pointed at someone's eye. If I turn them on, if I bring up red, we see little photons, little packets of red coming in. Someone's seeing red. Well, that's boring. Let's make things a little more interesting. I can turn that off and bring up green. He sees green. Okay, of course we know that. What if we have red and green together? Now he says, wait a minute, this is yellow. Our eyes only have receptors for red, green, and blue light. Yellow on the spectrum is between red and green. So if you see yellow light, then it's your eyes will say, well, I'm kind of seeing some red, I'm kind of seeing some green, I'm getting both of those there. Then your brain will see that yellow was there. You can actually fool your brain. If you send red and green light to it, it will see yellow. That's in fact what happens in a screen. If you see the yellow on this pixel, if you zoom in real close on that, you'll see that there's only red and green pixels that are on. When they're both on, then we'll see the red. Then we'll see yellow. If I turn on blue as well, all 3 come in. Now we're getting white. And we can play around with all kinds of things. I can turn off the red. We'll get blue and green together. Will give us a cyan color. Red and blue together give us a color. It's really not, this doesn't happen in nature. Your brain tries to figure out what the heck is going on. It will say, well, it's something in between. Let me call this magenta. So that's where the other color comes in. Different amounts of these, we can change the amount. You can play around with the quality of the color. If I put in more, if I have more red and less green, then I can make something more of an orange color. You can have lots of fun with this, lots of things. Students will spend, they spend a lot of time on it. Another demonstration, an easy one for you to do, is to play around with color and light. Here on this whiteboard, you can see all the different colors. I've written the name with the different colors from the markers, and obviously everything looks fine. That's because we're looking at it with white light. White light is nothing but a combination of all the colors of the spectrum. If we make a little tweak now, if I turn off that light and just turn on the red, where'd my red go? We don't see the red anymore because the red is reflecting off the whiteboard. So where we saw red from the red light, it's reflecting that, and the red is also coming off the whiteboard. So the red itself has disappeared. Notice the other colors now. They all look kind of black. We don't really see the other colors. They're absorbing the colors. Green is only reflecting green. It's absorbing the red, and so is blue. So they all look pretty much like black. Let's have a little more fun. Switch over to green. Where'd my green go? Green is gone. Now the red is there, but it looks kind of black. Green has disappeared. Our blue and black are still there. We can bring them all back if we turn on the white. Cool. One more for you. This is a cute little illusion. This is called the 3D miroscope. These are easily purchased. You can get them through Amazon or other sources. So let's take a look at our miroscope. This cute little thing. We see a little frog sitting on top of our thing. Oh, he's so cute. Reach over, give him just reach over and pet him. Say, oh, wait a minute. There's nothing there. It's gone. Nothing there at all. What's happening? What's happening is we've actually got two parabolic mirrors. If I take this apart, you can see the actual frog sitting down on the bottom of the mirror. Neat. I'm going to take Mr. Frog, put him off to the side for a second. I'll show you. You can have all kinds of fun with parabolic mirrors. It creates a real image. Let me see if I can get this in the camera here. So it creates an image. I'm seeing the lights from the ceiling here is creating a real image. It's actually floating up above my hand here. I can put my hand underneath it. If I bring my hand down, this works a lot better in real life, but you can see here as I come and approach this, you can reach out, you can shake hands with yourself. Students really get freaked out when they see this one. As they reach toward the parabolic mirror, all of a sudden the hand is reaching back and you see them jump away. Really cool stuff. So all kinds of fun things you can do with some very simple materials in the classroom. I have an absolute blast teaching science. I hope that you do too. So that's all I have for now. I wish you all the best in the upcoming school year. And again, well, that's all I have for today. If you have any other questions, I'd be more than happy to talk to you. Carolyn can get you in touch with me. I love teaching science. I love talking about it. I love talking about science and education. So I wish you best of luck with the new school year. We're already about 2 weeks in, so far so good. I really wish you all the best and take care.